All right. Hi. Welcome to Learning to Test Drive, a discussion about how to move from theory to practice. Thanks for coming. Before we start talking about test-driven development, I want to share some information about myself and why I'm devoted to testing it all. My name is Sean Frost, and I've been an Agile developer since 1999. When the consultancy I worked at decided they needed me to program more than they needed me to collect timesheets. I learned to code on the job, pairing with experienced developers who taught me the ways of object-oriented design and XP. I'd like to say that they taught me test-driven development as well, but we weren't really into that. We were quite proud of our automated tests, but we wrote them after the fact. Later, I started to call that test last if ever, as it became obvious that some logic was never represented in a regression test. Skipping down the list, I am non-binary, which has no bearing except that I'd appreciate it if you use they, them pronouns when talking to others about this presentation, whatever else you might say about it. Thanks in advance for that. Also, I like cats. Cats are great. Wearing cat earrings, even when they're being jerks. If you can love a cat that just knocked a glass of soda onto your laptop, you can accept darn near anything. Oh, right, and that third point there, and the big heart, those are adorable reminders that I need to tell you about my nearly tragic backstory about testing. Back in the early aughts, I was part of a team rewriting a browser-based patient care application in Java servlets. These weren't just any patients. This was for tracking transplant patients from candidacy through surgery and into continued care. This is a story about a donor heart. I was preparing to go into town for a show one Saturday night, and I got a call from the client's project manager. He told me that there was a heart available and that when the clinic tried to look up the contact information for the patient at the top of the recipient list, the site crashed. This was a technical manager who'd built the system we were replacing, but he didn't know how to find the data since we'd migrated it. I walked him through the SQL queries to find what he needed, and that was that. A bit of stress. Basically, things worked out, but I was a wreck. Lives literally depended on this application, and we'd shipped it out with a major bug in functionality that was needed for emergency situations. When we investigated the error on Monday morning, it turned out that it had specifically been my code. I'd never tested what would happen if a particular piece of data was missing. That detail had gotten skipped as I'd worked on a large feature juggling a lot of data and translations. So after that, I got way into TDD. Also flow cytometry, but that's another talk. The goal of this presentation is to offer some ways to learn test-driven development. These aren't a replacement for the practice, but an introduction to some techniques that can allow better understanding of test-driven development, as well as interim solutions to help migrate from test last if ever to designing your software through testing. Test-driven development can include unit testing and acceptance testing. This talk is focused on unit testing. I don't want to get into the weeds on this, as the assumption of this presentation is that you are already on board with at least the concept of test-driven development, but I do want to bring up a few points that will be important for this session. By test driving their solution, developers build confidence that their working code delivers on the required functionality as they are developing it. There's little doubt about when to run the application and verify behavior because they know when it should be fully ready. The happy byproduct of this approach is a suite of regression tests that can be run at any time and may be included as automated parts of both source control and the deployment pipeline, where they will likely be joined by other automated tests at a higher level. There's another aspect that we'll explore later, which is that test-driven code can be more modular in architecture. That depends a lot on learning to use the tests as an indicator for revisiting design. Keep that in the back of your mind as we launch into addressing how to approach the regression test aspect if you haven't yet developed the habit of test driving. Are we ready? Any questions so far? Not seeing any open questions. So, what's the difference between testing before and after coding? The automated tests that we run are to ensure that we haven't changed functionality unintentionally. They are checking for regressions in the code that have been introduced by changes. I've heard it referred to as test cement, and a lot of people apply it that way, pouring it over their code afterwards, like creating a mold. But tests are more likely to be comprehensive regression tests if they're written beforehand. That's because when only the code necessary to make the tests pass is written, the tests inherently cover all of the functionality. Things get a little tricky at the edges of the code base when interacting with third-party libraries or making network calls, but business logic code can be completely tested. So when you approach writing tests after the coding is done, how can you be sure that you're creating complete regression tests? When I was getting started on test driving my code, I would treat my implementation as a spike. If you're not familiar, the idea with a spike is that you are proving out an idea, not writing production code. You're meant to throw it out when you've learned what was needed. Why is it called a spike? I guess developers just love aggressive language. I was still learning to code in the first place, so I didn't want to delete the code, but I wanted to follow the spirit of removing it. What I did was to comment out everything that wasn't required by the compiler. I called compilation the first test. Then with those comments as a guide, I wrote tests that would allow each line to be uncommented. Before further discussion of how this leads to test-driven development, I'd like to show you an example of how this works. This example is based on a real piece of code that I encountered in the wild. I've recreated it here without object or parameter names that could identify the nature of the business. The structure of the code and nature of the testing is matched as closely as language differences allowed. Looking first at the left side, there's a lot of code, and clearly not all of it is necessary. We have some largely duplicated hard-coded values. There's a variable that's only set in one case. It could use some work. Now for the tests on the right. There are two of them, and the only thing they check is whether the incoming code affects the outgoing tag. Nothing else is tested, which makes the result of refactoring uncertain. We need to make it safe to clean up the logic, so let's comment out the implementation, leaving it there as a reference to ensure that we don't miss anything. Then run the tests and restore anything that's required. It turns out that we need to restore a few things. The conditional setting of value and a few versions of an outgoing request. No fields other than tag are tested. So I've put the others in as empty under each of their commented implementations. Oh, and the case where two outgoing requests are returned, yeah, only the first one is ever checked. So gradually building out the tests, we can restore all of the original code. Here's the two-test structure again with everything tested. Not only are we verifying all of the fields, but we're now looking at the second outgoing request that gets returned when the code is not ABC123. With confidence that we'll detect regressions, we can come back to our re-implemented code and restructure it. There are a number of hard-coded values that we see, some of which change depending on variables or order. There's some confusing business with the setting of value at the top. After every change, running the test tells us whether we've made a mistake. Otherwise, it's exactly the same process of changing the code as you might do without the tests, but with added confidence. One approach would be to reduce the method to the essentials. If the code is ABC123, create an outgoing request with tag CV1000. Otherwise, create one with an empty tag and add a second with different mappings. Details are removed to unexported functions, but anyone can read this and look into the specifics that interest them, such as these. These extracted methods are now just simple mappings, uncluttered of any logic whatsoever. The code is easier to read, and there are tests that will check for regressions. Code that we didn't even write in the real life instance this is based on was tested after the fact in a way that gained the coverage of test-driven development and allowed for redesign. Okay, so I said that this would get you to test driving your code, and so far all we've done is refactor. Our tests serve better as a regression suite now, but we're still writing the code the way we always did. What's different is that now we're feeling the pain of our design. To explain that, there we go. To explain that, I want to show you some code that I wrote recently. I was working through a coding kata on scoring a bowling game. In martial arts, kata is a repetitive exercise designed to make particular movements a part of your muscle memory, so you don't have to think to perform common actions. Programmers co-opted the term to code problems that can be performed repeatedly in order to make certain tasks part of your default behavior. A lot of people use this to engrade the red-green refactor test cycle, certain algorithms, or even just familiarity with their IDEs. Personally, I just think they're fun. The bowling kata is a favorite of mine because it starts off with a few very easy cycles of testing and coding, and then pulls the rug out from under you as soon as you start to handle strikes. Okay, quick primer on bowling. There are 10 frames. A frame consists of 1 or 2 rolls, depending on what happens in the first roll. If you knock down all 10 pins on your first roll, the frame is over and you move on to the next one. Otherwise, you roll a second time and then the frame is over. Simple, except now you have to score it. If you're like me, and it's a miracle if you knock down every pin in a frame, it's really simple. Just take the number of pins you've knocked down in the current frame, add them to the score of the previous frame. Your final score is simply a count of how many pins you knocked down over 20 rolls. If sometimes you manage to get all 10 knocked down over the course of a frame, but not all in the first throw, then you've got a spare. This is slightly trickier, but it's still reasonable. You just need to add in the number of pins knocked down in the first roll of the next frame. You also still need to add that in the next frame. And the spare frame's in an indeterminate state until you start the next frame. Okay, it's a little odd, but you just roll again, resolve the score of the spare frame, and you're pretty much caught up. So far, it's pretty easy to test and build incrementally. Now, say you're lucky or skilled or both. Your first roll of a frame, you knock down all of the pins. Strike, yes! Like the spare, you need to start a new frame to figure out your score for the strike frame. Unlike the spare, you need both of the rolls of the next frame. Or if you get another strike, that 10 points plus whatever you get in the first roll of the following frame. Perfect game is 300 points. I won't explain why. It's just part of what makes the scoring so tricky to implement. Now, I explained all of this so that you understand what is supposed to be happening in the code I'm about to show you, because it is unreadable. I worked through the bowling kata, dutifully writing a test before each bit of coding, but I did not let the pain of implementation deter me from my lack of design. I committed to only using the two methods mentioned in the kata's instructions: roll, which you use to report the number of pins knocked down in a single roll, and score, which reports the score at the end of the game. Beautiful, isn't it? Spreads over 2 images just to fit on the slide. I don't even remember now what some of these variables actually represent. If I were given a new requirement to return a message of how many rolls were needed to resolve the score as of the current frame, I'd have to start by figuring out what jerk wrote this, discover it was me, and spend some time reflecting on the error of my ways. Where did I go wrong? How did this garbage code get checked in? Well, first I was working alone, but that's another topic for another day. When I explained how I approached this, I told you exactly why it turned out to be a mess. I did not let the pain of implementation deter me from my lack of design. The first pain was fairly small. My rather simple implementation for scoring had to account for tracking spares. I now had to keep track of each roll instead of just keeping a running total. And I had to know when to add a roll twice. That was not a breeze, but it was still achievable with a small amount of time and effort. It already looked awful. It was adding logic for strikes that the pain suddenly grew to where I had to intentionally ignore it for the purpose of the experiment in declining to design. Everything became at least twice as complicated. I tried to detect strikes, but my spare logic broke because now there were two conditions that depended on whether all pins were knocked down in a frame. And it mattered whether it was the second roll that accomplished that. There was no frames object, so I had to keep track of what type of frame I was in while I'm scoring through iterating through a collection of rolls. When I say that it was painful, what I mean is that it took a lot of trial and error over an extended period of time to make a test pass. I'm not going to say that there's a hard metric for how long it should take to make a single test pass, but if you go from about 10 minutes for your first few cycles to several hours for the next, that's the pain I'm talking about. And that pain comes from the growing realization that something is wrong. Your normal experience of breaking the work into small tested pieces implemented through cycles of red-green refactor creates a sense of the proper cadence in your mind. And when you keep coding beyond that normal range, you learn to identify that feeling of uneasiness as a sign of trouble. Trouble that can be resolved by taking a step backwards and reassessing. Having barreled right through that pain, I've left the code in a functioning state with all of the tests passing, and after hours spent tweaking flags and tracking numbers, I'm understandably itching to declare the whole thing done. It works. It does what it's required to. The next person can fix it, or we'll put in a tech debt card to clean it up. Move on to the next story and push our way through the difficulties there in the same way. What I should have done is revert my code when I was having difficulty with the strike calculations. Arguably, I should have made an initial design pass before starting the kata, but it's never too late to revisit. Why was it so hard to make that test pass? It was hard because the function already had too many responsibilities. Look at this thing. At the top level, it's accumulating the scores of each frame into one total to return. The complexity is that there are at least 3 types of frames, and they all resolve the scores differently. Some of them require 1 or more additional frames in order to calculate their own scores. So we need to design. You could sketch UML diagrams with your partner or whatever you find useful. This was pretty small, so I chose CRC cards. If you remember, the first C is for class. So I jotted down some nouns in the system. We've got game and frame and pin and ball and roll, score, strike, spare. Oh, and tricky one, calculator. So now let's add the responsibilities and collaborators to those. After filling them out from everything and finding out that most of them didn't really do much, I settled on the biggest missing pieces being frame and calculator. Ball isn't directly used. It's sort of synonymous with roll for this purpose. Roll is a function on game that takes pin count, and frame holds up to 2 pin counts. Strike and spare are important, but they're basically a fact about frame that only the calculator needs to know. We could extract everything into classes, but let's start with frame and calculator. We use our rough design to build out a frame to plug into our code. It's pretty simple. It accepts rolls, answers if it's a strike or a spare, reports number of pins for each of the 2 possible rolls. A small object with simple logic, very much like those TDD examples you find online. So our simple frame has a lot of test cases. uh, all of the positive usages are there, along with some of the boundary conditions. We want to know that 10 pins in the second roll is a spare, and that 2 rolls that don't total 10 pins is not a spare. You'll notice that we aren't testing what happens if you add a third roll or a second one after a strike. That's because while implementing this, I started wondering about how to know when to create a new frame and added a method for indicating a frame is full. You can see that at the end there. Just as it's up to the calculator to ask if a frame is a strike or a spare, it will be the responsibility of the game, I decided, to create new frames as needed. Could I also test what happens if an extra roll is added anyway? Yeah. If this were a more complex system, I probably would. We only have 3 objects with clear responsibilities, and the existing tests in game should let me know if there's a problem in the usage of frame. I mean, essentially, this is just a refactor. If something breaks at that level when I plug in frame and calculator, I'd come back and tighten up frame to be more predictable under misuse. But for now, I'll trust the tests that it won't be needed. So implementing all of these test cases, we could make a frame, we could plug it into the game now, but that's going to take a bit of effort to make frames work with the existing calculations. We know we want to make a calculator, so let's just do that first. It needs to work on a collection of frames and know how to score a lot of conditions. In fact, some of what we want to test already exists in the tests on game. So let's write some tests for our score calculator. The cases that we're interested in are all after a full game. So let's move the 3 tests for full games of under 10 pins per frame, full game of spares, and full game of strikes. We can encapsulate all of the complexity of scoring inside of the calculator, swapping out resolver strategies, for instance, for our 3 cases. Now we can simply iterate over each frame, create the appropriate resolver for each, and pump the result of each rule into the set of them, letting each resolver decide what, if anything, to do with them. So is that an efficient design? No. But we're talking about a very small loop over a tiny set of data. Efficiency isn't as important here yet as code readability. Now we have a calculator that takes a list of frames and returns the score. That giant score method in game can be reduced to a single line that returns the score from the calculator given the game's frames. The frames themselves are created and populated by the roll method, which needs some slight logic that I've extracted into a method here to decide when to create a new frame. All of the tests in game should still run. In fact, some of them are now duplicated, so we can remove those. We've tested the calculator, so we know that given proper frames, it works. What we need here is assurance that the frames are being assembled correctly. To do that, we can just use the two weirdest cases, spares and strikes in the final frame. If it knows how to handle those, then we can be sure that it's correctly converting rolls into frames. So now we're done with the kata. We've met the requirements, created a regression test suite, and left behind code that could be improved, but is understandable and easily changed. If we receive a request to report scores while waiting for a spare or strike to resolve as indeterminate, then we have a much cleaner starting point for that change. If we need to report the current scores for each frame as part of a dynamic UI, then we've already broken out the concept of the frame. This was simply the solution I used when preparing for the presentation. There are a bunch of different designs that could work as well or better. What I wanted to showcase here is not this particular design, but the time spent to make it a purposeful one. So where are we at? It looks like all we've done is just a lot of refactoring. And yes, exactly. Writing tests first is not simply about the order of operations. It's a way to ensure that you're thinking about the long term while you're coding. Planning the tests and designing the code to enable easier testing ensures that you're meeting the current requirements and reduces the complexity of your system. It builds refactoring into your work as a precursor to adding functionality, rather than allowing it to accumulate as a bad debt. It raises confidence in the ability to make further changes later and reduces fear in estimates, helping to create a more consistent velocity. If you're having trouble figuring out how to do test-driven development, it's helpful to transition first to spike-driven development. Write your code the way that you're used to doing it, but rather than just pour test cement over it when you're done, really treat it as a spike. Comment it out or remove it to the extent that you feel comfortable. Save it to a scratch file or a branch, delete it. However you pull it out, only put it back as tests you write demand the code. And if you find that it's difficult to write those tests, step back and make a better design to implement. Don't be afraid to start with refactoring. As you get more familiar with taking your time to re-implement your spiked solutions, you'll start to wonder why you're spending so much time spiking in the first place. That's when you know you've developed a test-driven mindset. You can look through at the code, inspect the tests, design a solution, and carry it forward through refactoring in TDD, preferably with a partner. If you're interested in a more in-depth discussion on this subject or anything else software or team related, I welcome you to take advantage of our pro bono office hours. It's a 60-minute session where we do a deep dive into a problem you're looking to solve and help frame some solutions together. So you could shoot an email to hello@integral.io to set one up.